Greetings! Welcome to Electronics 2. This is lecture number 11 and I am Razavi. Today we will continue to look at differential pairs and go over some more examples of the bipolar differential pair so that we get comfortable with the equations that we have derived so far. And then we will start looking at the mass differential pair and see how that one behaves with respect to various types of input signals. Okay, so today we go over some examples regarding this differential pair, trying to see, for example, this small signal operation and how the equations that we learned last time help us quickly analyze the circuit. But before we go there, let's review what we covered last time. We looked at a differential pair in the small signal regime, and one important observation that we made was this: if the two inputs to the differential pair start with the same level and change differentially, so one goes up by delta V, one goes down by delta V, and these changes are small, then we saw that this node voltage does not change, so Vp is constant. Okay, so if Vp is constant with time, we can call that an AC ground in the small signal model. So we said we don't even bother drawing the small signal model of these transistors. We just know that from a small signal perspective, these two emitters are connected to node P and node P is grounded, so that's ground. Okay, this is only for small signal operation, meaning we are dealing with signals that are changing the input voltage. Okay, so we are not at the bias condition, we are looking at only the changes. All right, so then we saw that the differential pair for this type of input signal is turned into two half circuits. We have a half circuit here and a half circuit here. And these are pretty independent. So for this one, I can write a voltage gain from the input to the output, and same for this one. So we saw that for the circuit on the left, we have Vx is equal to the voltage gain of the circuit, which we know from Electronics 1 to be minus GMRC if the early effect is neglected times the input voltage. And same with Vy. So if I'm interested in the differential output voltage change, that would be Vx minus Vy, that's just given by minus GMRC times the differential input voltage change. So from a small signal perspective, the voltage gain of the circuit is given by minus GMRC. And this voltage gain is called the differential voltage gain because we're taking the difference between the outputs and dividing it by the difference between the inputs. Okay, so that is a nice and simple approach to analyzing these circuits, provided that they do have symmetry, as we saw before, and also the inputs change differentially and by a small amount. So today we will try to build upon these ideas and look at some other circuits that have a similar behavior. Okay, so let's go and look at one example. So here's the first example that we want to study. All right, so we got this differential pair, and let's pick some numbers. So I have picked these numbers. I'm assuming that IEE is 1 milliamp, RC is 1 kilo ohm, IS of the transistors is 2 times 10 to the minus 18 amperes. Remember where IS appears, right? IS does not appear in the hyperbolic tangent equation, but it appears in one transistor's characteristic. So we know that the collector current of any transistor, a bipolar transistor, is given by IS x of VBE over VT. So if we are trying to relate the bias current of a bipolar transistor to its base emitter voltage, then we have this IS here. Okay, that's where it appears. All right, these, and then let's see, what else did I assume here? Okay, so with these, our objective is determine the bias conditions of Q1 and Q2. So that's the first thing we want to do, A. Then we want to construct the input-output characteristic. So construct the input-output characteristic. And finally, we want to find the small signal voltage gain. So voltage gain, and by that we always mean the differential voltage gain. Okay? All right, so those are our objectives in this example with these numbers that we have. All right, so for bias conditions, let's see what we have. So bias conditions, we can say bias conditions means that we don't have any input signal, so meaning that V in 1 and V in 2 have a zero difference, so they are at the same voltage, at a convenient voltage, right? So there's a voltage here applied to both of them. You can assume that these are shorted. Remember, we had a common mode voltage, so that's the idea. And when these two are equal, the current splits equally. So each of these transistors carries half of IEE, and that is its bias current. So we have IC1 equals IC2 equals IEE over 2. Okay, so we found the collector current. What other values do we need? Well, let's try to find the base emitter voltage, right? So how do I find the base emitter voltage? Well, I know that they are equal, again, because we are looking at the circuit with no difference between V in 1 and V in 2. And we know that VBE is given by VT log of IC over IS. So I'll write that here so that we have that. VT is VBE is VT log of IC over IS. So IC is half a milliamp. IS is this much. We divide, take the log, multiply by 26 millivolts. That will give us 800, let's see, how much did I find here? 862 millivolts. So 862 millivolts. So that's the base emitter voltage. Okay, very good. So we found some of the bias conditions. Let's go and construct the input-output characteristic. So, for B, we know that the input-output characteristic looks like this. So if I'm plotting Vx minus Vy as a function of V in 1 minus V in 2, this is the large signal characteristic that we derived before, that hyperbolic tangent. So it looks like this, right? It goes like this and goes like that. Okay, how much is this value or that value? Well, remember this was given by the collector resistor, this load resistor RC, times the tail current. Because when we are over here, only one transistor is on, the other one is off. In this case, if you're over here, this one is on, this one is off. All of this current flows this way through node Y through RC. So this node voltage is equal to VCC because there's no current here. The difference between these two is given by RC IEE plus. Right? That's the level that we have here. And then over here, we have minus RC IEE. And each of these is given by 1 kilo ohm times 0.5 times 1 milliamp. So this is 1 volt minus 1 volt, and this is plus 1 volt. Okay? It makes sense. For example, if we are standing here, meaning that V in 1 is quite higher than V in 2, all of the 1 milliamp goes to the left, flows through 1 kilo ohm, generates 1 volt. So we have a difference of 1 volt from here to here, and we have 0 volts across this device because there's no current here. So the difference between these two is 1 volt. So that would give us this value here. Okay. All right. So that's what we get for the input-output characteristic. And let's try to find the slope in this vicinity, right? The slope is, if you remember, is minus RC IEE over 2VT. And with the numbers that we have, RC IEE, that's 1 volt divided by 52 millivolts. That comes out to be something like 19.2 with a negative sign. So that is the slope. The slope doesn't have a unit because we are plotting voltage as a function of voltage, right? So the slope is unitless. All right, so in part C, we want to find the small signal gain. Small signal gain, voltage gain, as we just saw, was equal to minus GM-RC, which also is equal to this number, right? So it's also equal to minus RC IEE over 2VT, and that gives us also minus 19.2. So that is the voltage gain of this differential pair. Okay, so in other words, if I put this differential pair in a black box and it has 2 inputs and 2 outputs, then I can call this an amplifier. An amplifier with a voltage gain of minus 19.2. All right, provided that when I apply an input signal between V in 1 and V in 2, so as V in 1 and V in 2 go up and down differentially, it's a small change so that we are going up and down around here. So we are in the linear regime of this characteristic. So our approximations are valid, and then this small signal number or this slope around here give us the voltage gain. Okay. All right, so that's a very simple example just to get started with these things. Let's see if there's anything else that we need to talk about here. Okay, let's go forward and look at this example. So here's our next example. So right now, this example that I'm going to show you seems not related to what we've been talking about here, and that's okay. So here are 2 resistors. R1 and R2, and we assume they are equal. Okay, this is like Circuits 101 question. All right, now I'm going to change this voltage by delta V in this direction. You want to call this maybe V in 1, and then V in 2 in the opposite direction. So again, V in 1 and V in 2 start at the same level. One goes up by delta V, one goes down by delta V. So if I call this node P, what happens to the voltage at node P? Can we predict that? This is something that we should be able to do from Ohm's law and KVL and KCL, right? We don't even need electronics for this. Okay, well, we can do a quick calculation and see what happens. Let's call these two R1 equals R2 equals R, right? So how much is the current in this direction after we have made this change? This side has gone up by delta V. This side has come down by delta V. So the difference is 2 delta V. We have 2 delta V volts from here to here. We divide that by the total resistance, which is R. So the current that flows is equal to 2 delta V divided by 2R. So delta V over R. Okay, all right. Now I'm going to multiply this current by this voltage to find the voltage drop from here to here. So voltage drop across R1, this is after we have made the change, is equal to delta V over R times R equals delta V. Okay, so what happened? As this terminal went from some value up by delta V, the voltage from here to here went up by delta V. So what can we say about this voltage? This voltage did not change, right? That's the only way these results will be consistent. If this voltage doesn't change and I raise this by delta V, the voltage across this resistor goes up by delta V. So Vp cannot change. So we say that Vp is constant. So this is similar to our analysis in the previous lecture about this node P, right? We also saw there that after we did the calculations, we saw that if this goes up by delta V and this goes down by delta V, and those are small values, then that delta V is entirely absorbed by VBE1, meaning that VBE1 goes up by delta V, so this node does not have to change. And it's the same story here. So when we have symmetry in the circuit and we make a differential change on the two sides of the circuit, we can say that the points of symmetry stay at this voltage that they are, meaning that they can be considered AC ground because their voltage does not change with time. So any point of symmetry we see in the circuit will follow the same thing. In some cases, like here, we do need the changes to be small and differential because this is a nonlinear circuit generally. But in this case, they don't have to be small, but they have to be differential. Okay, so that doesn't seem particularly exciting, but now let's go to the next example and see how this understanding helps us analyze a more complex circuit than this one. So let me go to the next page. Okay, so here's the next example that we are going to look at. Well, there's a resistor here. So V in 1 on this side, V in 2 on this side, RC, RC, X, Y, Q1, Q2. Let's call these RE1, RE2, And we assume they are equal because the circuit is symmetric, right? RE1 is equal to RE2, we'll call it RE. And we have a tail current, IEE. Okay, so we would like to find the small signal voltage gain of the circuit, differential voltage gain. So for small signals, Vx minus Vy divided by V in 1 minus V in 2. How much is that? All right, so the difficulty here is that we have added these resistors in the emitters of these two transistors. So what would you call the circuit anyway? You would call it the bipolar differential pair with emitter degeneration, right? Because these look like they are degenerating these transistors. So this term becomes more obvious very quickly as we analyze the circuit. All right, so how do I go about analyzing the circuit? Well, again, assuming that V in 1 and V in 2 change by small amounts and opposite and equal amounts, and given that these two resistors have the same value, we're going to draw a line of symmetry in the circuit. Okay, so here's a line of symmetry. And we say that because this point lies on the line of symmetry, for small differential changes at the input, this voltage will not change. So this voltage, if you want to call this node P, Vp does not change with time. And that means that P is AC ground. Okay? All right. Now, of course, you can draw the small signal models of these things and actually prove that this node doesn't change. Okay? So if you're interested, you can do that. But we'll just accept that this voltage does not change even with these resistors, assuming that the circuit is symmetric around this axis. Okay, so if this is AC grounded, I can draw two separate half circuits now, right? So one circuit looks like this. We have a degeneration resistor going to ground, RE1, and the other one is on this side. This is, of course, for only small signal analysis, RE2. So V in 1 and V in 2. And then this is X and this is Y. Okay, so now I have two half circuits and I can write the voltage gain of this half from Electronics 1. We know the voltage gain of a degenerated bipolar common emitter stage, assuming that the early effect is negligible. In that case, I can say that Vx over V in 1, the voltage gain from here to here, is equal to minus RC, this is RC, divided by 1 over Gm plus RE1. This is what we learned in Electronics 1. Okay, RE1, RE2, they are the same, right? RE. And we can write the same exact expression for this side. So the total differential voltage gain will be like this. So Vx minus Vy over V in 1 minus V in 2 is equal to minus RC over 1 over Gm plus RE. That is the overall differential voltage gain of the bipolar differential pair with emitter degeneration. All right, so that's pretty simple. Okay, so you can see that by identifying line of symmetry, we quickly reduce the circuit to topologies that we have seen before in Electronics 1. And so we don't really need to draw much of equivalent circuitry because these are just familiar topologies and we can readily write their voltage gain. All right, so let me give you a quiz at this point and see. Okay, so we would like to construct the input-output characteristic of this circuit. So construct the input-output characteristic of the degenerated differential pair. Okay, so let me just get you started on that, and then you can think about it. So we know that if I plot Vx minus Vy versus V in 1 minus V in 2, what we know is that, for example, if V in 1 is sufficiently higher than V in 2, then definitely this transistor turns on completely and this transistor turns off completely. So just like the case of no resistors here, all of this tail current will go to the left. And similarly, if this is sufficiently higher, all of the tail current will go to the right. That means that the extremes of the characteristic are similar to the case with no resistors here, right? The extremes would be here, this one and this one. So this is still minus RC IEE, and this is still plus RC IEE. You can see that in these equations, these values are independent of the emitter degeneration resistance. Okay, also we know that has to go through here, because if the difference between these two is 0, the difference between these two is 0, right? Because of symmetry. So it has to go through here. Okay, so it goes like this, right? And something like that. The quiz that I want to pose to you is, how does this characteristic change if RE, this value, is 0 or not 0? Okay, so consider two cases, RE equals 0, which we had before, and then RE is not equal to 0, is greater than 0. Okay, I'll give you 1 minute to think about that. Okay, so what do you think? Well, let's look at the slope in the vicinity of 0. The blue slope is how much? So let me go back to blue. The blue slope is the gain that we found without emitter degeneration. So slope, meaning the gain, was minus GMRC. Okay? Now, in the red case, when the resistance in the degeneration network is not 0, how does the gain compare? Well, we know from Electronics 1 that the gain is lower, because I can write this as minus GMRC divided by 1 plus GMRE. So it's the original gain divided by 1 plus GMRE. So in the red case, the gain has to be lower. We're talking about the gain without the negative sign. So if I change to red, I need a slower gain, right? I need a lower gain, so something like this. So as you can see, this has to go like that, and this has to go like that. So the extreme cases are the same, but the slope around the origin has changed. Due to degeneration, the slope has decreased. It's a less sharp characteristic. So here, the slope is given by minus GMRC divided by 1 plus GMRE. Okay, so that's what emitter degeneration does to the overall large signal input-output characteristic, right? You can see that the slope decreases. Now, which one of these versions, the blue or the red, is more linear? If you think about it, here we see that we quickly reach saturation, so here the circuit becomes nonlinear, whereas with the red one we have a wider range of being linear. So the effect of emitter degeneration is to give us a more linear circuit, because now we have a straight line for a wider range of voltages. So we say emitter degeneration improves the linearity. And this is a critical aspect of degeneration that we use extensively in circuit design when we want to improve the linearity of a stage. All right, so that's something that came out of this very simple observation. All right, let's look at another example. By the way, I noticed that there should be with time here. Please add this to make sure that everything is correct. All right, let's go to the next example. And in this example, again, we have a differential pair, and we would like to find its voltage gain. And it looks like this. We have a resistor here, as usual. We have a differential pair with a tail current. Okay, and we have X and Y as the outputs. And now we come along and place a resistor between these two, and we call it RL. Okay, everything else is the same as the original circuit. It's symmetric and everything, but we just added this resistor. And we would like to find the differential voltage gain. Okay, so how do I do that? All right, well, I know that for small signal analysis, this point is AC ground because its voltage is constant with respect to time, the total voltage with respect to ground, right? If the inputs change differentially and by a small amount. All right. Well, how about X and Y? If V in 1 and V in 2 change differentially, can I say that Vx and Vy also change differentially? Sure, right? So if V in 1 and V in 2 carry differential signals, so something like this, we have something like this here and something like this here, right? So when this goes up, this goes down, and vice versa. Then the same story happens on X and Y. Of course, there is an inversion from this base to this collector. So Vx will do this, and Vy will do this. I drew these taller because there is probably voltage gain from the input to the output. So if V in 1 and V in 2 are differential, so are Vx and Vy. Whether we have this resistor or not doesn't make any difference. Okay, so now that we know Vx and Vy change differentially, we can go back to something that we already observed about a resistor. Remember, we had that on the previous page here. So, oh, sorry, not here, here. So remember, we had two resistors, R1 and R2, from here to here. and the two voltages changed differentially. And we said that this point, the midpoint of these two resistors, is AC ground because the voltage does not change with time. Okay, can I do that here in this example or not? So let's see what I can do here. Well, I have only one resistor, not two. Right? The previous one had two equal resistors between this side and this side. So why don't we do this? Why don't we take this resistor and write it as the series combination of two equal resistors? I can do that, right? I can say something like this. This would be RL over 2, and this would be RL over 2. I'll put a dashed line here because I don't want you to get confused. So this is a replacement for that, right? So I can replace this with that, right? So I can replace this with this. We all agree, right? Because these two add up to RL. But now I have found a point of symmetry. This point. This point is symmetric. So if this side of the resistor goes like this, and this side of the resistor goes like this, the midpoint will not change. If the midpoint does not change, we can call it AC ground. So this point, let's call it something else, call it node A. Node A is also AC ground. So node A is AC ground. So take a moment to make sure you're clear on this. I replaced the single resistor with two, each one equal to half of that value. I know that RL over 2 in series with RL over 2 is the same as RL. But now I have created a point of symmetry. And I know that X and Y change differentially. One goes like this, one goes like this. So the midpoint of these resistors will not change. It will be AC ground. Okay, so we're going to go to the next slide and now draw the half circuit. Because, you see, this is AC ground, this is AC ground. So this part of the circuit now becomes independent of this part of the circuit. So let's go ahead and do that in the next slide. Okay, so here's what we have. So half circuit equivalent this is RL over 2. This is node A, which has turned into AC ground, right? And this is also RL over 2. And then of course we have these transistors, and this is also AC ground because, as we saw before, the voltage doesn't change. And this is RC, and this is RC. And node X is here, and node Y is here. Okay, so the half circuit of interest would be this part here. That's a simple common emitter stage. The signal goes to the base, comes out of the collector, and the emitter is at AC ground. At the collector, we have two resistors, RP going from X to AC ground and RL over 2 going from X to AC ground. So they are in parallel. So the voltage gain will be equal to minus GM of this transistor times these two in parallel. So it will be RC in parallel with RL over 2. Okay, that is the differential voltage gain of a circuit, of a differential pair that happens to have a resistor between here and here equal to RL. Now, why did we have that resistor there? Don't worry about it. But just as an example, this is how we approach it. This is how we solve the problem. So again, we're looking for a line of symmetry through the circuit so that every point on the line of symmetry becomes AC ground. Okay, very good. So we got that. Let's go over one more example. So you see what happened here, right? This is AC ground, this is AC ground. This emitter is AC ground, this emitter is AC ground. All right, okay. So is it okay if I place a wire from here to here? It's okay, right? Because these are all ground anyway. I'm just shorting this ground to this ground and this ground to this ground, right? So let's try to redraw the circuit and we would see what it looks like. So this brings us to the next example. Now this looks like a very different differential pair, but it's really the same thing. So I have a collector resistor of RC, and now I come along and deliberately add a resistor from here to here. And I call it RL over 2. Are these two circuits the same? This one and that one? Well, as far as small signal operation is concerned, as far as the small signal voltage gain, differential voltage gain is concerned, yes, they are the same, right? Because when I look at the small signal model of the circuit, this is AC ground, this is AC ground, this is AC ground. And that's the same thing as everything that here. In other words, if I agree with this, I must agree with that, right? Everything again is differential here. This goes like this goes like this, X goes like that, Y goes like this, not like this, the other way. So Y goes like that. So these are differential, this is AC ground, right? So these two resistors, which we inherited from here, would have the same role as here. So from a DC point of view, from a bias point of view, they are not the same, because there is probably some of this IE that's flowing this way and so on, but we don't worry about that. As far as the small signal voltage gain is concerned, these two circuits are the same, because you can see that here I connected these together and I connected them together here. Okay, so I won't bother. This is the same equation that applies here as well. But I'm going somewhere with this because this is not particularly exciting. What is exciting is this. Okay, I'm going to redraw the circuit. All right, so here's this circuit. And I will draw these resistors again in here. But I will give them a different name. They were called RL over 2. Now I will call them RO. Is that okay? And RO happens to be the output resistance of these transistors, meaning the early effect is not neglected. So if we assume that the early effect is not neglected, we have to worry about the output resistance of the transistor, which in the small signal model appears from here to the emitter, right, between the collector and the emitter. Okay, now given that this circuit turned out to be the same as this circuit for small signal analysis, and given that this circuit is the same as this circuit, because I just changed the names, then this circuit is the same as this circuit, because this point is AC ground, right? So I can write the voltage gain of the circuit based on only half of it. Right? So I can say that the voltage gain is equal to minus GM RC in parallel with RO. This is RC here, and this is RC here. So I just replaced this RL over 2. I changed the name to RO, so I just put it over here. So you see that in this step-by-step process, we managed to include the early effect without trying to prove that with these two resistors here, this is still AC ground. Okay, I didn't prove that directly. What I did is I started from here. In the previous case, these resistors did not go to the emitters in the actual circuit, right? They were just connected to each other. But we saw that in the small signal model, whether these are connected to each other or whether they're connected to here doesn't make any difference because these are all AC ground. So then we concluded that a topology like that, whose small signal model is the same as this, would follow the same equation. And if you change the name to this, it will still follow the same equation. So in the presence of early effect, the voltage gain is simply given by this. In other words, we found the voltage gain of a simple common emitter stage from electronics 1 with RO included and use that here. Okay, so that's what we get in this case. All right. Well, these were some examples of the bipolar differential pair to show us how we go about analyzing these circuits. Next lecture, we will start looking at the MOS differential pair, and we will see that almost all of the concepts that we have developed here are applicable to the MOS bipolar differential pair as well. So the time that's spent here, the energy that's spent here was worth it because later on we can reuse all these concepts for the MOS differential pair. We saw that if the differential voltage is large enough, all the current is steered to one side. It should be the same whether these are bipolar or MOSFETs, right? It's the same thing. And we saw that a small signal gain could be obtained if we recognize that this point is AC ground. That should also be applicable to MOS differential pairs because we didn't really assume anything about the actual characteristics of the transistors in that calculation, and so forth. So there are many interesting things that will come out when we get there. So this concludes the lecture today. I will see you next time.